Welcome to the 104th Theoretical Physics Colloquium by Professor Carl Bender, who is Wilfred R. and Ann Lee Conacher, Distinguished Professor Emeritus of Physics at Washington University in St. Louis. He's also a visiting professor at Heidelberg University and King's College London. He received his PhD from Harvard University, had a postdoctoral position at the Institute for Advanced Studies in Princeton, and then became a faculty at Massachusetts Institute of Technology. Since 1977, he is a professor at Washington University in St. Louis. Over the years, he received many awards and honors and distinctions. He is an elected fellow of the American Physical Society, of the Academy of Sciences of St. Louis, and elected fellow of the Institute of Physics in UK. He had fellowships from Sloan, Guggenheim, Lady Davis, Fulbright, Livermore, Rockefeller Foundations. He was the Ullum Scholar at Los Alamos National Lab in 2006-07. He received a Danny Hyman Prize for Mathematical Physics in 2017 and Alexander von Humboldt Research Award in 2019. He is currently supported by Alexander von Humboldt Foundation, Simon Foundation, and UK Engineering and Physical Sciences Research Council. He did some important professional service. He was the editor-in-chief of the Journal of Physics, A, Mathematical and General Physics, and his research interests are very wide in mathematical physics, non-Hermitian Hamiltonians, PT-symmetry, complex extensions of quantum mechanics, and many other things. And today he will be talking about parity-time symmetry. And with that, I'll give the microphone to Carl.
Okay, well, thank you very much. Thank you for the invitation. These are the acknowledgements, which you already mentioned, so I will skip that. I'll merely say thank you, Igor, for your invitation. Of course, I wish I were there giving this talk live. If I were, you would see something like this. And of course, at the beginning of every talk, you have to give an outline. And as I said, this is my talk will be in three parts: the beginning, the middle, and the end. Okay. Okay. So let me begin with a 30-second summary of what I'm going to say. As you know, energy in physics is crucial. When you measure it, you get a real number. So in quantum mechanics, we traditionally, since a long time ago, since Dirac, we assume that H is Hermitian. And what I'm going to argue today is that there's another, much less mathematical and more physical possibility that could replace the condition of hermiticity, and that is that the Hamiltonian is PT-symmetric. Okay, that's what I'm going to be talking about today. So this is going to be a talk on PT-symmetry, not in politics necessarily, but in physics. So to begin, what's so special about PT? So you should remember that in your elementary physics course, you learned that Newton discovered gravity. This is a picture of Newton sitting under an apple tree discovering gravity. But Einstein rediscovered gravity. He discovered that time is actually money. Okay. So Einstein told us that we should study the Lorentz group. The homogeneous Lorentz group is the set of all real 4x4 matrices that map the space-time point x, y, z, and t into x prime, y prime, z prime, and t prime, okay? But in such a way that you have this light cone condition, that x squared plus y squared plus z squared minus t squared is preserved, okay? Now, as I'm sure you all know, parity, which is space reflection, called P, and time reversal, called T, are elements of the homogeneous Lorentz group. And that's because P changes the sign of X, Y, and Z. And T changes the sign of T. But these are all squares. So the minus sign doesn't make any difference. And these transformations must belong to the homogeneous Lorentz group. Okay, very simple. So the homogeneous Lorentz group is a continuous group consisting of 4 disconnected parts. Okay, there is a subgroup called the proper orthogonal Lorentz group, and then there are all these elements multiplied by t, and then same elements multiplied by p, and the same elements multiplied by pt, and these are 4 disconnected parts. This and this and this are not subgroups, of course, because they do not contain the identity, but this is a subgroup. But although people didn't realize this in the early days, we now know that P and T are not fundamental symmetries of the world. And we learned that from Li and Yang and Cronin and Fitch. And so you might think that PT is not going to have any special significance because P and T are not fundamental symmetries, so why should P times T be? But it's very interesting. The complex Lorentz group doesn't have 4 disconnected parts, it has 2 disconnected parts. So if the complex Lorentz group are all complex 4x4 matrices that satisfy the light cone condition, and all these elements are continuously connected. So the elements in the proper orthogonal Lorentz group are continuously connected to these elements. These elements are connected to these elements, okay, along a continuous path, okay? So complex variables suggests that PT is connected to the proper orthogonal Lorentz group, but not P or T. So PT symmetry is deeply connected with complex variable theory. And in fact, this is the basis of the proof of the CPT theorem in particle physics. This is a long and complicated theorem. If you want, you can read Streeter and Whiteman and find out about it, but it needs a whole book to explain the CPT theorem properly. Okay, so the point here is that mathematicians find it interesting to extend the real number system to the complex number system. And that's because it helps to explain the real number system. But in our study of PT symmetry, what we're doing is extending conventional real Hermitian physics to complex non-Hermitian physics. And we're going to be studying the significance of this. So of course, you know that the real world, the conventional world is described by real numbers. For example, election results or IQ tests or even money. Okay, and indeed, this is a real quantity of money. Okay. However, complex mathematics is very powerful. It explains all sorts of things. It explains the convergence of Taylor series. It is used to determine the asymptotic behavior of real integrals. It helps us to sum divergent series. It explains real functions like the square root function and much, much, much more, which we could talk about sometime. But let me give you one, let's talk about one thing. Let's talk about functions, simple functions that need complex variables to explain them. And the simplest such function is the square root function. And the question is, why is it that the square root of 4 has 2 values, +2 and -2? Why are there 2 answers? And the reason is that the square root function is defined not in the complex plane, but on a Riemann surface. Okay, so what is a Riemann surface? A Riemann surface, in this case, is 2 complex planes that are cut and glued together. Okay, and each of these the sheets in the Riemann surface are numbered, sheet 1 and sheet 2. And the fact that there are 2 sheets explains why there are 2 possible answers. Okay, so that's what a Riemann surface is. And this has the topology of a Mobius strip. That is, if you go around twice, you return back to the starting point. At this point, for example, the square root of 4 may be +2. You now go around the origin, and now the square root of 4 is -2. But if you go around again, you come back to the starting point where the square root of 4 is plus 2. Okay, now that's just mathematics. Okay, but it's important to understand the complex plane when it comes to physics. These are examples of complex planes. Okay, so in school, you learn that in quantum mechanics, a particle in a potential well has quantized energy levels. So put it in this well, it'll have quantized energies. And you also learn that going from one level to another is a discrete quantum leap. But complex analysis gives you a much deeper understanding of quantization. So to explain a very simple case, I want you to imagine a two-state system having energies A and B. He doesn't understand what I'm saying, but I'm sure you do. So here is a Hamiltonian with the energies A and B. We can couple these states with a coupling constant G. Okay, and we can find the energies of this coupled two-state system just by taking this determinant, and it gives you a quadratic equation, and you solve it. And these are the energies. There are two energies, okay? And you notice that there's a square root function here. And there are square root singularities in the complex coupling constant plane at these points. These points are called exceptional points. They were originally called Bender-Wu singularities, which goes back a ways, okay? And these are the points where these two energies become equal, okay? They become degenerate. And the Riemann surface for this energy function in the complex G-plane looks like this. There are now two branch points, but it's still a two-sheeted surface because there's a square root function here. And what you see is that on this complex coupling constant surface, the energy levels are not discrete. Okay? You can go from one value of the energy and continuously deform in the complex coupling constant plane to the other value of the energy. Okay, so the energy levels are not discrete, not in the complex extension of the real axis. And what you see is that quantization is topological. Quantized energy levels correspond to discrete sheets in the Riemann surface. Okay? And
Carl,
what's more,
may I ask you a quick question?
sure.
When you're doing this complexification, you actually also making the energy complex, and so far you are not worried about that, right?
That's right. That's right. So this is the real axis. The real axis actually is over here. Okay, and on the real axis, that is when the coupling constant is real, the energy is real. Okay, but what we see is that there is an extended theory that lives in the complex plane. It isn't visible to us, but it's there. And that's because real functions have analytic extensions, whether they like it or not. Okay, and so what you see on the real axis is only a microscopic, it's only a set of measure 0 of the actual function that lives in the complex plane. We do this all the time in particle physics because we talk about complex extensions of scattering amplitudes and so on. Okay, S matrix theory is all about that.
Okay, that's fine.
So what you see is that quantization is topological. And these square root singularities over here and over here explain the divergence of perturbation series. And in fact, you can even use complex variable techniques to sum a divergent perturbation series. Okay, so in general, if you ask what sort of system are we talking about, I want you to imagine a parking garage. Okay, this is the real axis over here. Okay, and if you insisted on living in real space only, you would say this parking garage has discrete levels. Level 1, level 2, level 3, level 4, and so on. Okay, and they're discontinuous. But if you extend this into the complex plane, it's smooth. And the picture that I'm showing you is completely generic. Okay, this is nothing to do with 2x2 matrices. This is generic, even if the matrix is infinite dimensional. And so unlike what is taught in conventional quantum theory courses, energy levels smoothly deform into one another under analytic continuation. Okay, now this is, so far I've been talking about mathematics, but this is actually physics. And this, in this beautiful paper in PRL back in 2012, these people here, a big group of people, was able to study a system which was a microwave billiard, and they were able to vary the parameters of the problem and physically deform continuously from one energy level to another. And they were actually able to observe the fact that the energy levels are continuous deformations of one another. Okay, and this paper was followed by two more papers, actually in the same issue, or almost in the same issue here, in 2016, where they did an even more beautiful study of the analytic continuation of energy levels. But what I want you to notice here is that this system here has the word PT-symmetry in the title. That's the title of the talk I'm giving. And they studied a PT-symmetric system, which was a complex system. It was a deformation, a complex deformation of a Hermitian system, a physically real system. Okay, so what is PT-symmetric quantum mechanics? PT-symmetric quantum mechanics is what you get when you extend conventional quantum mechanics into the complex domain. And the point here is that if you respect PT symmetry, the eigenvalues can remain real, and more importantly, maybe, unitarity can be preserved even though the Hamiltonian is not Hermitian. So what is a PT reflection? It's a simultaneous reflection of space and time. Not space only, not time only, but space and time. Okay, so let me give you a very early example of a PT-symmetric Hamiltonian. This is it. This is a Hamiltonian that was studied by a number of people. Tan's group in Brown University, they were studying Region field theory. Bessis and Itzikson were studying it at Saclay, because this is a one-dimensional model of the Liang edge singularity, which I won't talk about today. When I first saw this Hamiltonian, I laughed at it because I said, this is ridiculous. I told the people who showed it to me, the way I see it, this theory is crazy. And that's because it's obviously not a Hermitian Hamiltonian. However, a few years later, I realized that this Hamiltonian, I was not thinking about this Hamiltonian. It just came back to me a few years later. But this Hamiltonian does have a symmetry to replace hermiticity, and that is PT symmetry. And that's because under P, X goes to minus X and P goes to minus P. But under time reversal, I goes to minus I. So if you combine P and T, you see X goes to minus X and I goes to minus I, and therefore this is a PT symmetric, although non-Hermitian Hamiltonian. So you might say, so what? Who cares? Okay, so I was interested, I should say, I was interested in looking at the eigenvalues of this Hamiltonian, which had not been studied before. And this is not an exactly solvable problem, okay? So you have to use some technique, and I like using perturbation theory to solve difficult problems. And the question is, why is that? Because if you have a frighteningly difficult problem, you insert a perturbation parameter epsilon, a small parameter, and you expand in powers of epsilon. And the advantage of doing this is that it converts a great big hard problem into a sequence of smaller and easier problems. Okay, so here's a sequence of much easier, smaller problems, okay, which you can solve one by one. Okay, so as an example, here's a very hard problem in principle, okay? If someone walks up to you on the street and says, find the real root of this polynomial, of course, if you did some numerical analysis, this is the real root, okay? But this is a quintic polynomial and there isn't any formula for the roots of a quintic polynomial. But you can use perturbation theory. So if you're a physicist, you would do maybe strong coupling perturbation theory. You put an epsilon in front of the smallest power of the field in a Lagrangian, the mass term maybe. And you expand in powers of epsilon. Here's the perturbation series. The radius of convergence of the series is 1.6. And of course, to recover the original problem, I set epsilon equals 1, which is inside the radius of convergence, which is good. You plug it in, you sum up the series. If you sum up these 6 epsilon to the 6th term, you get an error of 0.07%, which is great. Okay, so you're very happy. You might also do a weak coupling perturbation expansion, but as you may know, almost always a weak coupling perturbation expansion is a divergent series. And you can see the coefficients getting bigger and bigger. If you plug in epsilon equals 1 here, the radius of convergence is 0.08. And if you plug in epsilon equals 1, you get nonsense. But we know what to do. We know how to sum a divergent series. You can use Padé theory, for example, and that gives you an error of 1.2%, which is pretty good. Not as good as strong coupling, but pretty good. Or you could do something really clever. You could use exponential perturbation theory. You can put an epsilon up in the exponent here. And now this is not a coupling constant. What this epsilon is doing is telling you it's a measure of how nonlinear the problem that you're solving is. So when epsilon equals 0, this is a linear problem, and of course you can solve it exactly. And the answer is x equals 1/2. Okay, but if you expand in powers of epsilon, you get a series of coefficients that look like this. The radius of convergence of this perturbation series is 1. And of course, we want to set epsilon equals 4, which is outside the radius of convergence. But if you use Padé theory, you do better than both strong coupling and weak coupling perturbation theory. This is excellent. In fact, if you use a 6-6 Padé, you get an error of 0.00015%, which is really great. Okay. So do you remember what we were talking about? We're solving a difficult problem. Let me show you a difficult problem in physics. This is the Thomas Fermi equation, which describes the charge density in a nucleus. Okay, and it is a non-linear second order differential equation. If you make a radial, you make an assumption of radial symmetry, rotational symmetry about the nucleus, okay, and there are some boundary conditions. The exact solution looks like this. The charge density rapidly falls off at infinity, but nobody knows how to solve this problem exactly. It's an impossible problem to solve analytically. However, if you simply insert an epsilon in the exponent, then this problem looks like this. And we want to know what happens at epsilon equals 1/2. But when epsilon equals 0, the problem is linear. And this already looks like a good approximation to the linear problem. And in fact, on the back of an envelope, you can calculate the answer accurate to better than 1%. And it takes you just 2 or 3 minutes. Okay, so you remember the problem that I was solving a long time ago? I told you about it. This is the problem here. You insert an epsilon in the exponent. Why do I do this? Because now you notice that when epsilon equals 0, this is just the harmonic oscillator. And furthermore, unlike many perturbation theories which violate the symmetries of the problem, for example, in electrodynamics, you might violate gauge invariance if you do perturbation theory, unless you do it very carefully. In this problem, for all real values of epsilon, you have PT symmetry, and that's because I goes to minus I and X goes to minus X. Okay, so epsilon measures the departure from an exactly solvable theory, which is the harmonic oscillator. And if you solve the problem, you are doing a PT-symmetric calculation. Remember, what I want you to remember is that PT-symmetric Hamiltonians are complex deformations of Hermitian Hamiltonians. So you begin with a Hermitian Hamiltonian and you introduce a deformation parameter epsilon. So this is the deformation parameter epsilon. Okay, just take a look at what happens here. Here is the Hamiltonian. This is the deformation parameter. And as a function of epsilon, so when epsilon equals 0, these are the energy levels of the harmonic oscillator: 1, 3, 5, 7, 9, 11, and so on. And as epsilon increases, the eigenvalues all remain real and positive and discrete. Okay? And if you would like to see a real, this is a very difficult thing to prove. The first proof of spectral reality came in 2001. It was given by Dory, Dunning, and Tateo, and you can read these papers. These are long papers. This is a real tour de force of mathematical physics, mathematical analysis. There are some interesting special cases, of course. The first case is the problem that I set out to solve, which is this. That's the case for epsilon equals 1. What is very interesting is the case for epsilon equals 2. This is the theory that we're solving. And this is an upside down potential. And what I'm telling you is that this upside down potential here at epsilon equals 2 has positive energy bound states, real positive energy bound states. So they are stable states. So I am telling you that with an upside down potential, which looks like a repulsive force, it can have stable bound states. And I will explain this to you a little bit later in this talk. But this is certainly a surprise, a really big surprise. Okay, but complex variables is a very powerful and very deep theory, and it gives you a direct explanation of this, of what is going on. Okay, so just for you to remember, PT-symmetric Hamiltonians are complex deformations of Hermitian Hamiltonians. You can begin with a Hermitian Hamiltonian, introduce a deformation parameter epsilon, and now you've got a non-Hermitian PT-symmetric theory, typically. This is a complex deformed squirrel. Okay, here's a complex deformed frog. I like this. This is a complex deformed parrot, and you can see the PT in it. You know, it's right there. So here's a very simple example. Take the harmonic oscillator, and instead of doing a multiplicative deformation, let's just do an additive deformation. Let's add on Ix multiplied by a parameter epsilon. And you can solve the Schrodinger equation subject to these boundary conditions. And these are the eigenvalues. And I want you to notice that these eigenvalues are real. Even though this is a non-Hermitian complex Hamiltonian, the eigenvalues are real. You can do this yourself in 2 minutes. Okay, and the picture I'm showing you is generic. This is instead of deforming a harmonic oscillator, let's deform an anharmonic oscillator in the same way. And again, the eigenvalues are all real and positive and discrete. Here's another case. This is the Hamiltonian p to the 4 plus x squared. And let's deform it. And again, the eigenvalues are real, positive, and discrete for real positive epsilon. And here's a really fancy case. Okay, here's a PT-symmetric Hamiltonian. And again, the eigenvalues are real and positive and discrete. Okay, so if you find this interesting, you can read a 3-page article on this. This is a very short article with no equations that I published in Europhysics News back in 2016. And if you turn to the article, which is called PT-symmetry in quantum physics, you'll see on the front page of the article a picture that I took. And this is probably the most exciting thing that ever happened to me. I've been a mathematical physicist my whole life, and I never thought that anything I was ever going to do was possible to measure in a laboratory. But here it is, after I had published my first paper on PT symmetry about 7 or 8 years later. That was the first appearance of papers with experimental measurements. This is an simple optical tabletop experiment. It was published in PRL, and they observed the system, and it had all of the properties that we predicted. So this is very exciting to me. So I had a wonderful time there. That article was followed up by another article in Nature Physics with an even better experiment, which made even more precise measurements of PT symmetry and PT symmetry breaking and so on. I found this very exciting. And that back in 2015, these experiments and many, many, many other experiments were responsible in part for this cartoon that appeared. It was a cartoon back in 2015 in Nature Physics. The title of the cartoon was Top 10 Physics Discoveries of the Last 10 Years. Okay, and every one of these pictures was a discovery, an important physics discovery in the past 10 years, but every one of these is a cartoon, so it has to be a pun. Okay, so this is the Higgs bison, not the Higgs boson. Okay, but I was delighted to see that up here, there was a picture of parity-time-symmetry and optics. Of course, they left off the I from party-time. So that's what they came up with. But they celebrated this as one of the top 10 physics discoveries, which was wonderful. And this is reflecting all of the experimental and theoretical work that had been done since the beginning of the study of PT symmetry. And in fact, it's being done all over the world. This is an example of PT symmetry in China. There are a lot of papers on PT symmetry coming out of China. If you're Chinese, you may not see this. But I'm sure if you're not Chinese, you do see it. If you need help, there it is. This means this is the character for place. So this is the toilet place over here. Okay, so why is it that upside down potentials, which are PT symmetric, so I showed you a minus x to the 4 potential, why is it that although this potential looks unstable on the real axis, why is it that it has a real positive discrete spectrum? How can that be? And complex variable theory explains why such a potential has stable quantum bound states. Okay, so to explain, let me show you a very simple case of simple harmonic motion in the complex domain. So remember what they teach you in the first 2 weeks of an elementary freshman physics course. They talk about a particle on a spring. The particle goes back and forth on the real axis. As you are taught, the particle goes all the way out to the turning point. It stops, it turns around and goes back again. It goes to the other turning point and it goes back and forth. And they tell you this is simple harmonic motion. And they tell you that there are classically allowed and classically forbidden regions. Okay, so these regions out here are classically forbidden. This is classically allowed. Why are these classically forbidden? Because these turning points happen when the particle is not moving. So they solve the equation E equals x squared. And so these points lie at the point x equals plus or minus the square root of E. Okay? So if x is bigger than the square root of E, x squared is bigger than E. But if x squared is bigger than E, then p squared is negative. How can p squared be negative? That's impossible. Okay? So it's a classically forbidden region. Okay, and if you don't understand this, this is an example of classically allowed and classically forbidden regions. Okay, now, however, what we can do is extend the classical harmonic oscillator into the complex plane. We don't care if p squared is negative in this classically forbidden region over here and over here. Okay, if p squared is negative, it just says that p is pure imaginary. So if we draw the coordinate, instead of talking about the coordinate axis, we talk about the coordinate complex plane. All that it means is that out here, particles are moving in the pure imaginary direction. And if you solve Newton's second law, classical equation of motion, and you allow for complex solutions, you will see that this back and forth motion is not the only motion. A much more interesting motion is out here. The particle is going this way, and it goes in a large ellipse in the complex plane. It is bound, it is in a bound state, and it's going around in the complex plane. And in fact, what this means is that for any point here, we have an ellipse. And as you approach this turning point, what this particle, this back and forth motion that you learn about in freshman physics is actually a degenerate ellipse. The particle is actually going infinitesimally above the real axis, whizzing around the turning point and going infinitesimally below the turning point, like this. That's the actual motion of the particle. By the way, these orbits are not Keplerian orbits because these turning points, by the way, are the foci of these ellipses. They play a very important role. And what we learn is that these orbits are not Keplerian because Cauchy's theorem tells me that, this is the Cauchy integral theorem, tells me that, in fact, the period of this motion is the same for all ellipses. It doesn't matter which ellipse you're on. It always takes the same amount of time to go around a closed orbit. Okay, now this is just the harmonic oscillator, but what I'm going to do is to raise the value of epsilon. Instead of talking about epsilon equals 0, I will increase it smoothly and gradually. When I reach epsilon equals 1, I get this cubic PT-symmetric Hamiltonian. The orbits deform smoothly as functions of epsilon. Here are those two turning points which have moved downward below 0 in the complex plane, and the ellipses deform into these shapes. These are approximate ellipses, if you like, okay, but they're still closed orbits, and the time of flight for every one of these closed periodic motions is the same. The period is always the same. It's a function of epsilon, but it's always the same for any given value of epsilon. Okay, so we get classical trajectories in the complex x-plane. When you reach epsilon equals 2, here are the turning points in the lower half plane. Here are the orbits, the deformed orbits, okay? And we have to ask the question, a very, very difficult question that is too difficult to answer using real variables alone. And this is where the power of complex variable theory comes into play. You see, on the real axis, classical particles in this upside down potential roll down to infinity, but they get there in finite time. They take only a finite amount of time to reach infinity, and that time is t. So the question is, where is the particle at t plus 1? That's a simple question in real analysis, and we cannot answer that question without knowing about complex analysis. So using complex analysis, what I will do is look at larger and larger orbits to see what happens as I approach the real axis here. And if I do that, what I find is that as the orbit gets closer and closer to the real axis, the particle whizzes off at great speed into the complex plane and returns back to here. And the bigger the orbit, the faster the particle is going. And as you approach the real axis, what happens is that the particle rolls off to infinity. It infinitesimally fast goes whizzing around in the complex plane to minus infinity and comes right back up to the origin. Now, the particle is going very, very slowly at the origin, and it's going infinitely fast at infinity. So if you ask, where is the particle at any given time, it is most likely to be found very, very close to the origin. In fact, you can ask, what is the probability of finding the particle as a function of space, as a function of x, and the particle is in a very localized place, okay? The particle is very unlikely, in fact, 0, the probability is 0 of finding it at a great distance from the origin. It is most likely to be found in the vicinity of the origin. This is the classical probability density, okay? And so what we have is the particle in a dynamic bound state, okay? So what is really happening here is that the particle is moving very slowly at the origin. It whizzes around in the complex plane and then moves very, very slowly at the origin. So what you see is that a static instability that you learn about in freshman physics becomes dynamically stable in the complex plane, just like a bicycle or a top. You know, when a bicycle is moving, it becomes stable. When a top is spinning, it becomes stable, even though when it's not spinning, it just falls over. Okay? And of course, we can quantize that motion in the complex plane just by writing down a WKB integral. And if you do this integral, you get, with very great mathematical precision, you get the values of the energy levels, and those energy levels are very well approximated by WKB, and they are real, positive, and discrete. Okay, so the instability, the static instability at x equals 0 is tamed. Complex analysis allows us to tame instabilities that you think are there because you are only living in the real world, but in the complex world, those instabilities become stable. So physical systems that seem to be unstable can actually become stable in the complex domain. And the question is, why is there no instability? And the reason is that, you know, if you extend the real numbers to the complex numbers, you lose the ordering property of real numbers. Everything about real numbers is also true of complex numbers, except for one thing. With real numbers, you can say greater than or less than. So you can talk about instability, meaning that, you know, when the energy is below 0, you say the system is unstable. Okay? But you can't use those words if you're talking about complex analysis because you can't say one complex number is bigger or smaller than another complex number. So physical systems that look unstable may well become stable when you treat them in the complex plane. Okay, so I want you to go back and look at that picture I showed you. This is the Hamiltonian with epsilon. Here are the eigenvalues. And you notice that when epsilon is real and positive, the eigenvalues are all strictly real and positive and discrete. Looks like a conventional bound state system in quantum mechanics. But you see something funny here. When epsilon is negative, the energy levels are deforming as a function of epsilon, and they become degenerate at a point here, and then they disappear. And this pair of energy levels becomes degenerate and it disappears and so on. What is going on here? So what is going on is that they haven't disappeared. It's just that they have become complex conjugate pairs. And so these points are called exceptional points, and they're the place where a pair of real positive discrete energies become degenerate and then go off into the complex plane. So we call this the region, we call this region here the region of unbroken PT symmetry. And here we call this the region of broken PT symmetry because for values of epsilon in this region, some of the energy levels, say for this value of epsilon here, real, 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 and then all the rest of the energies are complex. So we call this a region of broken PT symmetry, and this is called the PT boundary. This is a PT phase transition where the energies go from being all real to partly real and partly complex. So this is a phase transition, and we have a theory with complex eigenvalues along with the real eigenvalues here, but all real eigenvalues here. And this is the case, this is a theory that looks like a conventional Hermitian theory, but this is a strange theory with complex energies and real energies mixed. Okay, so PT symmetry does not conflict with conventional quantum theory, but it's weaker. The condition of PT symmetry is weaker than Hermiticity because if you have a Hamiltonian that's Hermitian, all the eigenvalues of a Hermitian Hamiltonian are real. So for PT symmetric Hamiltonians, only the secular equation is real, and therefore the solutions to this secular equation may be all real, and that's the unbroken PT symmetric region, or some of these eigenvalues in the secular equation may be complex. And there are those two possibilities. You could, PT symmetric theories can have an all real or a partly real spectrum. Those are the two possibilities. Okay, so again, this is an unbroken PT, and over here is the region of broken PT, and there's a phase transition in between.
Can I ask a question?
Yeah.
Why you call it broken PT? Because Hamiltonian remain still symmetric under PT.
Right.
You still have IX going back to itself, right?
That's correct. So the Hamiltonian itself is still PT symmetric, as you say. Okay. However, the solutions to the Hamiltonian are violating the condition that we want to live in a world with real energies. We don't want to live in a world, at least at this point.
But that's not symmetry broken, it's our desire is broken.
Yes, but the symmetry is broken because if you look at the eigenstates of the Hamiltonian, not the eigenvalues. So we say it's broken because the eigenstates themselves are not symmetric under a PT reflection.
Spontaneous broke.
That's exactly right. It's spontaneously
Okay,
broken. That's exactly correct. Thank you for the question. That's right. So what I would say is that Hermitian Hamiltonians are boring because the eigenvalues are always real and nothing interesting happens. But PT-symmetric Hamiltonians are astonishing because there is a transition between parametric regions of broken and unbroken PT symmetry. And this is very easy to observe experimentally. And that was what was observed from the very first experiment that I showed you before. So we can have a broken and an unbroken region, and we have a phase transition, which is very easy to observe in the laboratory. Okay, and I want to give you an intuitive explanation of the PT transition. Okay, so I want you to imagine that you have a closed box and you're pouring stuff into this box. It's very simple. Okay. So a closed box, you're pouring stuff in. What are you putting in? You could be pouring water into the box. You can be pouring energy. You could be putting particles in the box. It doesn't matter. The one to describe the state of the box, you only need a 1-by-1 Hamiltonian for this system. Here's the Hamiltonian. It has this is just a 1-by-1 matrix. A is real, B is real. And the fact that there's a complex part corresponds to the fact that stuff is going into the box and the amount of stuff in the box is increasing with time. Okay, so this is radioactive undecay. Okay, but now I want you to consider this a system with two non-interacting closed boxes. This box has gain, this box has loss, so we're putting stuff into this box and taking stuff out of this box. So now the Hamiltonian for this combined system is a 2-by-2 Hamiltonian. This has a positive imaginary part, a negative imaginary part. Stuff is going into this box and it's coming out of this box. By the way, this box is not in equilibrium. This system is not in equilibrium here, but this is a PT-symmetric system because under parity, you interchange these two boxes. But under time reversal, the stuff going in turns into stuff going out, and the stuff going out turns into stuff going in. So this is a PT-symmetric system, but it's not in equilibrium. Okay, and the eigenvalues, as you can see, are complex. Okay, so this is a broken PT-symmetric system. However, we can couple these boxes. Okay, we could put a pipe here. If you're pouring water into this box, it can flow through the pipe into this box where you're taking the water out. Okay, whoops, you're taking the water out of this box. Okay, and so this pipe has a coupling constant depending on how thick the pipe is, how much stuff can flow through the pipe. And this is the Hamiltonian for this coupled system. And this Hamiltonian is not Hermitian, of course, but it is PT-symmetric. And if you want to check that it's PT-symmetric, remember the T is complex conjugation. Parity is this Hermitian matrix. And under P times T, this is this Hamiltonian is symmetric. Okay, now let's find the eigenvalues of this Hamiltonian, and you already know how to find the eigenvalues. We just take the determinant, we get this quadratic equation, we solve the equation, and these are the eigenvalues. And you notice that there's a transition at G equals B. Okay, and the energy is real if the coupling constant is big enough. Okay, so if the pipe allows a fast enough flow, the energies become real and the system is in equilibrium. But if the pipe is too narrow, the energies are complex. Okay, so the system is in equilibrium for sufficiently large coupling, and that's when the eigenvalues become real. Okay, so what we have here, what we see here is that PT-symmetric systems lie between closed and open systems. Okay, so a Hermitian Hamiltonian typically describes a closed system. Non-Hermitian Hamiltonians, for example, in scattering theory, describe an open system, a PT-symmetric system sits between these types of systems because it's an open system. Stuff is going into the boxes and coming out of the boxes, and yet it's behaving as if this is it's described by a PT-symmetric Hamiltonian. And I like this these PT-symmetric systems. They're very interesting. I like them so much that I'm wearing my PT shirt here. Okay, that's these are PT-symmetric systems. You know that there is that they are voting right now on PT symmetry in Brazil. There's a PT party in Brazil, and we hope that the PT party comes into power, and that, well, I hope that Bolsonaro goes running off into the distance, into the complex plane. Okay, so there have been lots and lots of experimental studies of PT-symmetric systems. This is just a short list of some of the beautiful experimental work that has been done. And I wonder, can I have about 5 minutes more? I just want to show you some pictures of some of the papers that have been published. I'm not going to give
5 minutes is okay.
Yeah. So this is what I showed you before. This is the first observation of the PT transition between broken and unbroken PT symmetry in that laboratory using an optical experiment. But here are some of the other papers. This is a study of PT symmetric diffusion. This is a study of PT symmetric optics done at Caltech. This is a study of PT symmetric superconducting wires. And you notice here are the real energies splitting into a complex conjugate pair. Here is that paper I mentioned to you before, PT symmetry and spontaneous symmetry breaking in a microwave billiard. Here is PT symmetry breaking in optical scattering systems done at Yale. This is a study of photonic lattices. Here's a study of exceptional points in lasers. This is parity-time-symmetry for photonic lattices. This is done in Germany. Study of another study of PT-symmetric superconductivity. Here's a study of PT-symmetric NMR, which was done mostly in Beijing. Here's a study of PT-symmetric metasurfaces in Texas. Photonic crystals at Stanford. There's a study of relativistic non-Hermitian quantum mechanics. Study of PT-symmetric wireless power transfer. And I won't take the time in my talk to explain this to you, but this is absolutely beautiful stuff. I invited Shanhui Fan, is brilliant. He's at Stanford. And I invited him to come to Washington University to give us a colloquium on his work. It is absolutely brilliant work. And if you want to ask me about it after my talk, I would be very happy to explain his experiment to you. It's just stunningly beautiful. And this is a very elementary paper. This is a PT-symmetric electronic circuit. You remember that those two boxes I showed you with water going in and water going out? Well, this is an oscillator inductively coupled to another oscillator over here. And one oscillator is coupled inductively to a source, so energy is going in, but the oscillator also has energy going out because there's a resistor in the circuit, okay? So this is a PT-symmetric system where energy goes in, energy goes out, and you can see the PT-symmetric transition occurring, PT symmetry breaking. It's a beautiful piece of work. It was given it was called by the APS exceptional research, a very, very elementary paper. And I was so impressed with this beautifully simple paper that I decided to build a mechanical analog of that circuit. And all you need is two pendula, one pendulum having friction, the other pendulum being driven magnetically. And again, you can see the PT phase transition. Those are the equations for that coupled system of pendula, and these are PT-symmetric equations with a PT phase transition. Okay, and this is the same thing, except at a very, very, very sophisticated level. This is a whispering gallery, an optical whispering gallery, where you have an optical beam going around and around and around in a whispering gallery, and another whispering gallery coupled to it. And you shine a laser on this whispering gallery, and this whispering gallery has natural optical loss. So you have two coupled whispering galleries like this. And again, you can see the PT phase transition. It's beautiful. So this is an overview of my talk. I don't know whether or not I've succeeded in putting some of you to sleep. Maybe I have. Hopefully some of you have stayed awake and heard most of the talk. I don't know, could I mention one last theoretical issue? Would that be possible? Can I take about a minute or so to, or are
sure, I
people...
suppose. We already have plenty of questions, but if it's just a minute, go ahead.
Yeah, so I was going to just mention one theoretical application. This is one of my favorite field theories, so this is a little bit more sophisticated. This is a very early model quantum field theory that was proposed by T.D. Lee. It's called the Lee model. He proposed this back in 1954. Historically, people were studying perturbative renormalization, which is the big mathematical problem in quantum field theory, and he wanted to understand renormalization in an exactly solvable model. Okay, and so this is a very, very simple, beautiful model field theory. So there are three particles in this model, and he called them V, N, and theta. Okay, so this is like a pi plus turning, to a pi basically, turning into decaying and giving off a theta particle here. And, we could call this maybe a neutron turning into a proton and an electron. And then the proton and electron can turn back into a neutron. Okay, very simple three particle system. This is the Hamiltonian for the system. The Hamiltonian is the energy of the system is simply the number of V particles, N particles, and A particles multiplied by their masses. And this is the interaction Hamiltonian that says you create a V, but you destroy an N and a theta, or you create an N and a theta and destroy a V. That's it. Okay, and this system is exactly solvable. And T.D. Lee went through the renormalization procedure, and you can do mass renormalization, coupling constant renormalization, wave function renormalization, all in closed form. Beautiful. Well, physics evolves very quickly. And 1 year later, Shalane and Pauli, who was very scary, showed, nope, this model is wrong. And why was the model wrong? The model is wrong because when you do coupling constant renormalization, the bare coupling constant is in the Hamiltonian, but you can express the bare coupling constant exactly in terms of the physical coupling constant G, which you measure by just measuring a scattering amplitude. Okay, and the connection between the two is this very simple equation. And what you see is that if in the laboratory, if G is too big, like here, then if G is bigger than this number, then G squared is negative. This is a plot of G squared as a function of G. But if G squared is negative, G is imaginary. And if we go back and look at the Hamiltonian, the Hamiltonian has an imaginary term in it. So this is a cubic Hamiltonian with an imaginary coupling constant, and that's not Hermitian. And indeed, what Shalane and Pauli showed is that ghost states appear, okay, which is very serious. And so you're violating hermiticity and you lose unitarity. Terrible, okay? And if you read about this in Barton's book on field theory, he says a non-Hermitian Hamiltonian is unacceptable, partly because it may lead to complex energy eigenvalues, but chiefly because it implies a non-unitary S matrix, which fails to conserve probability and makes a hash of the physical interpretation. So this is a disaster. And so renormalization can turn what looks like a Hermitian Hamiltonian into a non-Hermitian Hamiltonian, just renormalizing it. And this is a really hard problem, and lots of people worked on it. Pauli worked on it for a very long time. Heisenberg worked on it, Wick, Sudarshan, but they didn't solve the problem. But we solved it because we realized that this is nothing but a cubic Hamiltonian with an imaginary coefficient, coupling constant. And back in 2005, my students and I published a paper where we showed there is no problem at all. This is a unitary theory, except you have to define the time evolution operator very carefully, and you can show that the eigenvalues are real and also that probability is conserved if you develop the theory of unitary time evolution for PT-symmetric theories. And so we were reviving quantum theories that were thought to be dead. Okay, and PT-symmetry has come to the rescue. Okay, and this is a remarkable fact that renormalization is very dangerous because it can produce what looks like non-Hermitian Hamiltonians, okay? But in fact, there is no problem. Okay, that's just a taste of what you can do with some of the theoretical work. And I hope you found this interesting.
Okay, thank you so much. Thank you, Carl, for a nice presentation. Let's go to questions because we already have quite a few people who want to ask questions. Let's start with William Horowitz, please.
Sure.
Thank you so much. So very interesting talk. I haven't fully digested it, but one thing that you pointed out, yes, one massive advantage of Hermitian Hamiltonians is you get real eigenvalues for energy, and we definitely want real eigenvalues. But
well,
we also want,
I want to comment about that. Actually, I mean, if you ask what are, I mean, if you look at the universe and you look around and you ask, are the eigenvalues actually real? Well, the proton doesn't decay, maybe, and electrons maybe don't decay, so their energies are real. But most of the particles that you know about, most of the states that you know about, do not have real energies because they decay. So it may well be that we live in a world that is PT-symmetric, that it has a broken PT symmetry, and so I mean, it's true that in a closed system, the eigenvalues are all real. But maybe our system really does have complex eigenvalues given by the fact that particles decay, but please go on. Sorry to interrupt.
Yeah, when I measure my age, unfortunately, it's a real number. But in any case, so the other thing that's really important and valuable when it comes to Hermitian Hamiltonians is that we're guaranteed a complete eigenenergy basis. Have you investigated the spectrum of these PT-symmetric Hamiltonians?
Yes,
are they complete? Thank you.
And yes, so it becomes a more complicated problem in the broken PT-symmetric region. But in the unbroken PT-symmetric region, where all the eigenvalues are strictly real, you can have continuous eigenvalues, but all real eigenvalues. You have, indeed, you have a complete set of states. You have a Hilbert space. You have all of the properties that you would like a Hermitian Hamiltonian to have, okay? It's just that, I mean, I think we have to agree that the condition of hermiticity, which is what we grew up learning, you know, when we took our quantum mechanics courses, we learned that one of the axioms of quantum mechanics are that the Hamiltonian should be Hermitian, okay? Now, I just want to point out that all of the other axioms that you learned about quantum mechanics are very physical sounding axioms. I mean, you learn that the energy should be bounded, you know, the energy of the states of your system should be bounded below, that you should have unitarity and so on. These are all physically oriented principles, okay? But there's this one axiom that you learn, which is pure mathematics, which is that you learn the condition of hermiticity, which is a very sophisticated condition. In fact, what you really learn is this condition of self-adjointness of vectors, of operators acting on vectors in Hilbert space. And that's a very fancy mathematical condition, and it's higher mathematics. It doesn't sound like physics to me. Whereas PT-symmetry is physics. Okay, here we're just talking about symmetries of the universe. And that's why I began this talk with a discussion of you know, of the Lorentz group and P and T and so on. This is physics. This is not mathematics. And that's why I really like this condition of PT symmetry. It has a much better taste in my mouth. It's not this strange external mathematical condition that seems to come in from the outside in order to make your system work well. Okay, but yes, indeed, in the region of unbroken PT symmetry, you can show that the states are that the states of the system are complete. You can expand your vectors in your Hilbert space as an infinite sum over the eigenvectors, the PT-symmetric eigenvector, the eigenvectors of your PT-symmetric Hamiltonian.
Okay, Carl, we have a lot of questions, so if you could answer the questions a little more quickly, so that
I will try.
Let everybody else get a chance because of time.
Yeah.
Paul, please go ahead. You're next.
Sure. Hi, Carl.
Hi.
Great talk, as usual. I have a very quick question concerning the case of the Hamiltonian, the PT extended Hamiltonian with epsilon is 2, so where h is p squared minus x4. And my question is that, so normally if I look at that Hamiltonian, I would say that it's completely unstable. The potential is sort of flipped sign, and this sort of theory should not exist in a sort of general sense. And
Right.
sort of, this argument that, okay, because for a complex Hamiltonian, there is not a real numbering property.
Right.
So maybe that's why. So my question is that if I sort of construct such a system with a potential that's minus x to the 4, should I expect this system to exist in sort of a stable sense? So you said there are real spectrum of eigenvalues, or should I expect this to not make sense? So I'm confused.
Right. So you're not the only one who's confused. Okay. I mean, this is very interesting because the question you're asking is, wait a minute, doesn't this have unstable states? Okay. And the direct answer to your question is that a Hamiltonian does not have a unique spectrum. It just doesn't. Not until you give me the boundary conditions on the Schrödinger equation associated with that Hamiltonian. Okay, so a given Hamiltonian corresponds to a given time-dependent Schrodinger equation, but that time-dependent Schrodinger equation can have many different spectra depending on the boundary conditions. Now, if you want to impose, if you want to, let's see, can I take about a minute to answer this question, because this is a really great question, and let me see if I can. Let me stop sharing. Okay, so let me give you an explanation to this question, because this is really a central issue. How shall I explain? Let me give you a simple, very simple question that you must never ask your students when you're giving them a qualifying exam. Okay, it's a very simple sounding question, but it's a very hard question. Suppose we have a harmonic oscillator Hamiltonian, which is p squared plus omega squared x squared. Okay, just this Hamiltonian. Okay, and we know what the eigenvalues of this Hamiltonian are. The nth eigenvalue is 2n plus 1 times omega. That is the exact spectrum of the harmonic oscillator. Okay? Now, here's the question that you should never ask a student on a qualifying oral. You can say to the student, wait a minute, what happens if I rotate omega so that it becomes negative? So in other words, in the complex omega plane, I will begin with a positive value of omega, and I will rotate it around in the complex plane to a negative value of omega. Okay? Now it's the same Hamiltonian because there's an omega squared here. But all the eigenvalues now seem to be negative. So are you telling me that that same Hamiltonian has negative eigenvalues? Or what? I thought it only had positive eigenvalues. What's going on here? Okay, and the answer is you must be very careful. So evidently, so the correct answer to this question is yes, indeed, this Hamiltonian has two different spectra. One of them is positive, one of them is negative. The positive spectrum is obtained by imposing boundary conditions that the eigenfunctions vanish on the real positive axis and real negative axis. But if you impose the boundary conditions that the eigenfunctions vanish on the positive imaginary axis and negative imaginary axis, you find that the eigenvalues are discrete and negative, real and negative. Okay, so in fact, the Schrodinger equation, the time-independent Schrodinger equation, which is this, this is the time-independent Schrodinger equation here. That time-independent Schrodinger equation has two completely different eigenspectra, one positive and one negative. Okay, now indeed, the same is true for virtually any Hamiltonian. And in general, for the anharmonic oscillator, say, there may be many different spectra. There could be 3 or 4 or 5 spectra. There could even be dozens of them, depending on the nature of your boundary conditions. And if you have PT-symmetric boundary conditions, the eigenvalues typically are real if you have a theory which has an unbroken PT symmetry. Okay, now physically, the question is, I understand your question. I can tell you a lot more in private, but I won't take the time. But what you could ask me is, how do I observe this positive spectrum? Okay, and it turns out that one of the conditions of PT symmetry is that the potential becomes reflectionless. Okay, reflectionless scattering was studied for the case of lasers at Yale, when they were studying PT-symmetric optical potentials, and reflectionlessness was observed by me early on, about 12 years ago or something, in a paper that I wrote with Michael Berry and another guy. Okay, and we pointed out that to see the PT-symmetric real eigenvalues, you have to do a scattering problem and look for reflectionless transmission. So let me just tell you why, physically, why this upside down potential has bound states. The reason is, I think you probably know that staircase potentials in general can have bound states. Even, a staircase potential is one that goes down and down and down all the way off to infinity. How could it have bound states? Okay, and the answer is, if you have a particle sitting at the top of the staircase in the middle of this potential, a wave will propagate out to infinity, but when it hits the edge of the staircase, it scatters off the tip of the staircase and some of the wave comes back. And then it keeps going out and more backscattering occurs. And as it goes out, parts of the wave scatter backward toward the origin, and eventually nothing ever reaches infinity. Okay, now that is a discrete version of the minus x to the 4 potential. In the case of the minus x to the 4 potential, it becomes so steep that there is backscattering toward the origin physically occurring. Okay, and you can have a system in a bound state when the energy of the original state that you put in this potential is such that as it tries to leak out to infinity, it all scatters back. Okay, to observe those energies, all you need to do is to take a potential, of course, not an infinite potential, but a finite minus x to the 4 potential, put it in a box, okay, take an incident wave and demand that if a particle is incident upon this upside down potential, it propagates out to infinity with no backscattering. And this will happen at a discrete set of energies. And those are the PT-symmetric bound energies. Okay, they are real. There is zero backscattering. You have 100% transmitted wave. And if you want to read about this, we just about 2 weeks ago put a paper on the web describing the details of such an experiment, and you can read about it. Okay, and you can see how to see that scattering, that positive discrete spectrum. Okay, and it has to do with perfect transmission. Okay, that's the physical property that you're looking for to see these energy levels. Okay.
Okay, we are really running out of time. I wonder if we could take at least one more question because of the lateness of time. We had the next person having some problems with the microphone. So probably Paul, just go ahead and ask your question and I'll read the next question if we still have a little time later.
Mm-hmm.
Okay, hi, Carl.
Hi, Paul. By the way, Paul, it's really, really nice to see you. Thank you so much for coming to the talk.
Well, I know your talks are always exceptionally perspicuous. I'd like to ask a perspicuous question. This is something that occurred to me on somewhere during talk. You said that going from the real numbers to the complex numbers, it loses the greater than or less than inequality. No, I was thinking of an analogy that if you go from something quite like the real numbers, namely the field of rational numbers, and you go where there is definitely greater than or less than, and you go from that to the p-adic number field, then it also loses the simple greater than or less than. I wondered if there was any way of making an analogy and whether that has any possible physics in it.
Yeah, Paul, that's a really interesting question, and I haven't thought about it. I don't know whether perspicuous or perspicacious is the right word to use here, but
Perspicuous is the right word.
yes. But anyway, I mean, the answer is I don't know. That's a really interesting question. It is so you know, if you ask what are the properties of the real numbers, they have the standard, you know, the commutative law and the associative law and the distributive law and the ordering property. That's the characteristics of the real number system. And you lose just the ordering property when you go to the complex numbers. When you go to a higher number system, you know, the complex numbers consists of two parts, a linear combination of two real numbers. When you go to a combination of four, you lose commutativity, okay? And when you go to the, that's the quaternion, then when you go to the octonions, you also lose associativity, and all you have is distributivity. And, you know, people have studied octonionic quantum mechanics. I assume that there are papers on, you know, on the system of p-adic numbers, but I have never gone into it or thought about it. Maybe someone should do a piece of work on it. I think that would be really interesting.
Okay. Sorry, you wanted to say something? Well, sorry, I interrupted you.
No, I mean, I'm sure that Carl and I can talk about this for hours, but I don't think we have time, so we should switch.
Okay.
Yeah.
Anyway, I wanted to use this opportunity, first of all, and make sure that I thank Carl again for the presentation. It was absolutely fabulous, and obviously the interest from questions shows that that was really very nice and useful.